Section 4.1, exponential functions and their applications. We're going to see how we apply or what are exponential functions, how to work with them, and why are we learning them, how we apply them. If we go back to previous chapters or sections, say we had f of x equals 2 to the x, or another function g of x equals 5 to the x. If I just switch the base and the exponents, let's say I'm going to get L of x, which is x squared, or vice versa, h of x is x to the fifth. So notice the stuff on the right side, we are familiar with this. Those are polynomials. Their bases are variables, and the exponents on the top are just numbers. Those are constants. When we switch them or flip them, switch the base and the exponents, we get 2 to the x, 5 to the x. So I'm getting a number to an x. Those are called exponential functions. Those are called exponential functions. Those are polynomial functions. So polynomial functions, they have to have a base of a variable. But exponential, they have a constant as a base. 2 to the x, 3 to the x, 1/2 to the x. So we can introduce a definition. Exponential functions are those that are written in the form y equals, say f of x equals a to the x. A is called the base, x is the variable, like the exponent. And this a must be constant, like a number. Again, let's call it base. It has to be bigger than 0, but it can be 1. It's bigger than 0, but it can be 1. To do some applications to this, what about if we are asked to find 3 square? Or maybe like 1/2 square? How do you find something like this? Or 5 to the negative 2. To evaluate each one, 3 square means 3 times 3, which is 9. This one is 1/2 times 1/2, which gives us 1/4. The next one, we can rewrite it by bringing that down, 5 square, because that's over 1. So that becomes 1 over 5 times 5, which is 1 over 25. Now, if we need to apply it more to a different example, let f of x, a function, be given as 3 to the x, another function g of x, 4 to the 3 minus x, and a third function h of x, which is 1/4 to the x power. And we are asked to find the value of first one, f of 3. F of 3. So what is f of 3? We are going back to the function f of x and replace x with 3. So that gives us 3 to the third. So 3 to the third is 3 times 3 times 3, which is 27. If we need to find another one, g of 2. What is g of 2? G of 2 is 4 to the 3 minus 2. That's 4 to the first power, which is 4. Another example, g of 3. G of 3 can be written as 4 to the 3 minus 3. 3 minus 3 is 0. Anything to the 0 power is 1. What about another example? H of negative 2. H of negative 2, going back to the function h, so that's 1/4 to the negative 2. We learned a property before about exponents, which says to make the negative positive, you flip the fraction. So 4 squared, which is 16. Now, what other things we can learn about this exponential functions? One thing very important is how do we graph exponential functions? Let's say the simplest example I can choose is y equals 2 to the x. And one thing comes in mind is to pick values for x and get their corresponding y values. So for example, 0 usually is in the middle. We take 2 values above 0, 2 values below 0. And now we're going to substitute these values in to find their corresponding y values. 0, 2 to the 0 is 1. 2 to the first power 2. 2 squared is 4. This one is 2 to the negative 1, which is 1/2. 2 to the negative 2, 1/4. So that gives me enough points to graph or to sketch the graph for this function, which is going to go 0, 1, 1, 2, 2, 1, 2, 3, 4. Negative 1, 1/2. Negative 2, 1/4. So it's going to go like this. That's the graph for this function. Notice how the graph is approaching the x-axis, which has equation y equals 0. This line is called a horizontal asymptote. So y equals 0 is a horizontal asymptote. Y equals 0. For the x-intercept, we're analyzing the function or this graph. There's none, no x-intercept. For y-intercept, there's only one y-intercept, 0, 1. Domain is all real numbers, negative infinity to infinity. Or people write like this, means all real numbers. Range is also 0 to infinity from here, or you can say y bigger than 0. That's domain and range. Also, this function, it is an increasing function. It keeps going up and up. And maybe you hear like people say the growth or something exponentially. It's growing exponentially, means it's increasing like this, like the graph you saw. Also, it is 1-to-1. 1-to-1 means it passes the horizontal line test. If you draw horizontal lines, it will only cross the graph at most 1 point. One thing, as a note, I'm going to introduce it here. For f of x to equal a to the x, there are two things. If a bigger than 1, the function is going to be always increasing. If a is less than 1 but has to be bigger than 0, the graph is going to be always decreasing. So before you start graphing the function, you will know if this is going to be an increasing or decreasing function. And if we look back at the one we had, 2 to the x, 2 was bigger than 1. That's why it was increasing. Now what we're going to do is, I'm going to take the graph of the function we got, 2 to the x. So use the graph of y equals 2 to the x to sketch a graph for number 1, y equals negative 2 to the x. Negative 2 to the x. So what does the negative do here? If you remember from previous sections, this negative means I made y negative y, y negative y. So this tells us that we need to get the graph of this, we reflect the graph of y equals 2 to the x about the x-axis. About the x-axis. So the x-axis becomes what I call a mirror. So the original graph we graphed earlier for 2 to the x was this. this was 1. When we reflect this about the y-axis, this is gonna go this way, down, 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 down. This is -1. This is y equals -2 to the x. So that's how we got it. Without plotting points, we're able to graph this one. What about another example? The same thing, use the same original function and then make x -x. In this case, the negative on the top tells me to reflect because x became -x. Reflect the graph of y equals 2 to the x about the y-axis. So y-axis will be the mirror. So I'm going to redraw this again. The original graph. This is 1. So this is y equals 2 to the x. I'm going to reflect this about the y-axis. So this point stays the same. This is going to go down. This is going to go up. So this is y equals 2 to the -x. So this means if you fold the paper along the y-axis, the two graphs will coincide. And then for the previous one, if you had to fold it along the x-axis, the two graphs will be identical, like coincide with each other. What about something like this? This one, what we do if there's a change on x, as you could see on the top, there's a change on x here. So what do? We always set that on the side equals 0, add 1 to both sides, so x is a +1. X +1, x always means either to the right or to the left. That's what x means, right or left. So that shifts the graph 1 unit to the right side. So let me always graph the original one. This is the original. So I'm gonna pick 5 points, about 5 points, 1, 2, 3, 4, and 5 on the original. And I'm gonna shift each one to the right 1 step. So that becomes here, this becomes here, this becomes here, this becomes here, this becomes here. So that's gonna go like this, up. So this is y equals 2 to the x minus 1. So all I did, I just shifted the graph to the right 1 unit. Now, what about if we need to graph a function from scratch? Say y equals -1/2 3 to the x. To do so, we're gonna pick or choose the table here. Find values. 5 values are sufficient to graph it. 0, 1, 2, -1, -2. And if I pick the values up, let's say I'm gonna start with x equals 2. Let's see what we get. Y equals 1/2 3 squared -1/2 times 9. Half of a 9 is 4.5. So this is -4.5. If I choose x equals 1, we get y equals -1/2 3 to the first power -3/2, or -1.5. Next equals 0, we got y equals -1/2 3 to the 0, which is -1/2. What about x equals -1? Y equals -1/2 3 to the -1. -1/2 times, this is 1/3, so that makes it -1/6. X equals -2. Y equals -1/2 3 to the -2. -1/2 times 1/3 squared 9, so that's -1/18. And now we're gonna plot these points on the graph. Let's see how the graph's gonna look like. X, y, and 0. I'm gonna start with 0, -1/2. Say here. 0, -1/2. These are the points increment-wise by 1, 2, 3, 4, 5. Next one is 1, -1/2. 1, negative 1/2. So here 2, negative 1, negative 2, negative 3, negative 4, negative 5. This one, and somewhere here negative 4.5. And when we chose negative 1, it was negative 1/6. So negative 1, negative 1/6, and then the other one here. So you can see that's the graph dysfunction. Now to analyze this, for x, the x-intercept, none, y-intercept, 0, negative 1/2, domain, all real numbers, negative infinity to infinity, range from negative infinity to 0, from the bottom up. And we had y equals 0 is a horizontal asymptote. Another good thing that we can add to this is that if what we called it before when we did polynomials, as x approaches infinity, what happens to the y? We call them endpoints. As x goes to negative infinity, what happens to the y? Where is the y traveling? So as the graph goes to the right side, like as x traveling to the right side, so as x going this way to the right side, what's happening? The function is going down. Going down to where? Well, keep in mind on the x-axis there's always negative infinity and positive infinity. On the y-axis, negative infinity, positive infinity, like that. So as x value increases to the right side, the graph is heading down. The graph is heading down toward negative infinity. So then this means this is negative infinity. As x goes toward negative infinity, so to the left side, the graph is approaching y equals 0. Okay, so more than this, to apply more about transformations, let's say you're asked to describe the transformation. Transformation means, is it translation? Are you moving to the right, left, up, down? Are you doing reflection? That's called transformation. So describe transformation using the graph of y equals 5 to the x. It's not asking us to graph it, just say how you get it from this graph. So the first one would be 5 to the x plus 2. Number 2, y equals negative 5 to the x. Number 3, y equals 5 to the x minus 3. Number 4, y equals 1/5 x. So how do we get the graph of number 1 from 5 to the x, which what we call the parent function? That's called the parent function. So how do we get the graph from that one? Okay, so the first graph here on the top, do you see the change x plus 2? We can take that x plus 2 on the side equals 0, then solve, and x equals negative 2, as you can see. So this tells us the negative, x means right or left. Negative means to the left. So what do? We shift the graph. We shift the graph of y equals 5 to the x, 2 units to the left side. For the next one, the negative, if you remember negative y means we reflect about, means reflect the graph of 5 to the x about the x-axis. Here, if you really cover 5 to the x, you got y equals negative 3. Y means up and down, up or down. Negative means down. So this tells us to shift the graph of y equals 5 to the x, 3 units down. For the next one, this one here, we can rewrite this one first as 5 to the negative 1 to the x. It's 5 to the negative x. So the negative x means right or left. That's what x means. So if we need to shift it or having that negative on over there, this means the negative tells us to reflect about the y-axis. Reflect about the y-axis. Now, let's look at another graph. A graph for another function. Let's say we would like to graph y equals 3 to the negative x. So keep in mind first, this is the same as 1 over 3 to the x or 1/3 to the x. They all mean the same thing. Now this 1/3, it's between 0 and 1. Remember, that's the a value. This is the a value. A value. So the a value is between 0 and 1. So we expect the graph to be decreasing, to be going down. So let's see how that works when we pick values for x and get their corresponding y values. So if you substitute 0 in, anything to the 0 is 1. 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. If you put negative 1 in, 3 to the positive, that's our 3, and then that's 3 squared, 9. So now we're gonna graph this. 0, 1, say 0, 1 here. 1 and 1/3. 2 and 1/9. Negative 1 and 3. Negative 2 and something up there. So this is gonna go all the way down. So do you notice how it's a decreasing function? The asymptote stayed the same, y equals 0, same intercept, no x-intercept, 0, 1, y-intercept, domain all real numbers, range from 0 to infinity. Now the question is, how do we find the limit as x goes to infinity of 3 to the negative x? What is that going to be? And same thing when x goes to negative infinity. So this is basically the end behavior. So as we travel to the right side, as x growing up, the graph is approaching y equals 0. And as we travel, or the x value travels to the left side, the graph is going up to infinity. So that helps to find what we call the end behavior. So if we need to look at another example about the end behavior, so let's say randomly, a graph is given. A graph of a function is given. This is 2 here, and then you have some function that goes this way. Say this is 3, the origin. Always label everything possible. The question is, what's the limit of this function? I'm going to call it f of x as x approaches infinity. And what's the limit of the same function as x approaches negative infinity? Well, as x approaches positive infinity, so as you travel to this side more and more, the graph is going up to positive infinity. And as you travel to the left side, more and more to the left side, the graph is approaching y equals 2. Those are called end behavior of the graph. Note, just to recall something here or introduce it, pi, we know the pi is 3.14. And we have another letter e, which is similar to pi, that goes forever, is about 2.7. Okay, about 2.7. So we have been graphing 2 to the x, 3 to the x, 3 to the negative x. So the base has been like 2, 1/3, 3, 4, 7. What about if the base is e to the x? How does the graph look like? Well, let's go through the chart again here. 0, 1, 2, negative 1, negative 2. So if you substitute 0 in, what do you get? E to the 0 is 1. e to the first power is e, which is about 2.7. And then e squared. This one, if you put on the calculator, you'll get about 7 point something. But we don't have to really know it because I think the first 4 points will be enough, sufficient to graph this. E to the negative 1 or 1 over e. E to the negative 2 or 1 over e squared. So now we are going to plot the points. The first one is negative 2 and 1 over e squared. Negative 1 and 1 over e. 0, 1. So it's growing this way. 1 something. 2.7. So the graph is going to go up this way. Similar to 2 to the x. Right? Similar to y equals 2 to the x. Because 2 to the x and 2.7 to the x both are kind of very close to each other. So in this case, domain is all real numbers, range goes from 0 on. We are interested to see the end behavior of e to the x as x approaches infinity. As you go more toward the right, it goes up, and the limit as x approaches negative infinity for the same function is approaching 0. That's pretty much about the graphs of these exponential functions. Now we're going to see how we apply them. For example, when it comes to equations, solving equations. To do so, the first thing I want to remind you about, if we have an equation in this form, a to the m equals a to the n, means if they have the same base, so, and this is an equality, then the exponents must match. So m must equal to n. How do we apply this? Let's say we're asked to solve 10 to the 3x equals 100,000. Well, I need to see if I can make the bases match. Let's keep this as is. This can be written as 10 to how many zeros? 1, 2, 3, 4, 5. 5 zeros. Now the bases match. Since the bases match, we can set the top equal to each other. So then x is 5 over 3. Okay, so this is just an equation I was able to solve because the bases match. Now, exponential functions, they have, or exponents in general, they have properties. Let's recall there's 7 of them. I'm going to recall about 5 of them, or 4. Those are the most important that we're going to be using the whole time. Let's recall 5 of them. A to the negative m, it's 1 over a to the m. If you are multiplying same base, you add the exponents. If you're dividing same base, you subtract the exponents. If you have a to the m all to the n, you multiply m by n. And the last one, anything to the 0 power is 1. To apply these properties to exponential stuff, let's look at solving more equations. Let's say we are asked to solve 3 to the negative x is 1 over 27. Let's see how we do this. The first thing is, any big numbers you see like 27, we're going to prime factorize it. What is prime factorization? Is write it as a product of primes. 3 and 9, 3 is a prime. 3 and 3, 3 and 3, both are primes. So the left hand side stays the same. The right hand side, instead of 27, I'm going to write it as 3 to the third. We have 3 identical copies of 3. So 3 to the negative x, one last thing to do is bring this up, becomes a negative 3. So when you bring something from the bottom up or the top down, we change the sign of the exponent. It becomes from positive to negative or negative to positive. Now the bases match. Since the bases 3 and 3 match, we can set the exponents equal to each other. Multiply by negative, and that will give us what we need, x equals 3. Let's look at another example. What about if it comes like this as a fractional stuff? Equals 125. Again, we take the big number, prime factorize it. By 5 is 25, prime, 5, 5, prime, prime. For the one on the left side, what we can do is bring this up. So make it 5 to the negative 1 all to the x. And the 125 is 5 to the third. I'm trying to get the bases to match. What can I do with these two? Based on one of the properties, you can multiply them. So 5 to the negative x equals 5 to the third. Now we can set the exponents equal to each other. And multiply by negative, you get x equals negative 3. Let's look at more difficult example. So let's say 4 ninths all to the x times 8 over 27 raised to 1 minus x. All this equals 2/3. Now look at the bases. 4 over 9 is not the same as 8 over 27. It's not the same as 2/3. But 2/3 is the smallest. And notice 2 and 3, both of them are prime numbers. Maybe I want to think to make these bases here to match these two highlighted ones to match with 2/3. Can I write 4 over 9 as 2/3? Yes, it's 2/3 square, all raised to the x power, times this is 2/3 to the third power, raised to 1 minus x. And keep this the same, to the first power. What can I do here now? The next thing I'm going to do is I'm going to multiply these two and these by one of the properties. So 2/3 raised to 2x times 2/3 raised to 3 times 1, 3, 3 times x, 3x. And keep the right hand side the same. Now all the bases match, but the property I give you earlier has to be one thing on the left side and one thing on the other side. Here, these two bases match and I'm multiplying. So what I can do, I can add the exponents, like so. Now notice how we have only one exponent on the left side and one on the right side. What we can do next is set the top equal to each other. Combine like terms. 2x minus 3x is negative x. Subtract 3 on both sides, we get a negative 2. Therefore, x is 2. What about looking at one other example about equations, but make it more difficult? 2 times 2 to the 2x equals 4 to the x plus 64. So what makes this challenging is that there's no way to make it one thing equal one thing right away. But I see 64, 4, 2, 2, like all of them, they kind of like related in a way or another. So what I'm going to do here, there's one way to approach it is to rewrite this as 2 squared to the x. Because if you go backwards, you can multiply the exponents, 2 times x. Keep this the same. Why did I do this? I did it because 2 squared now is 4. So this way it matches the other 4 on the right side. And what does that tell us? This tells me I have 2 copies of 4 to the x and there's 1 copy on that side. So I can subtract this copy on both sides. So I get all the x's on one side. 2 copies minus 1 copy. That gives us 1 copy of 4 to the x equals 64. Now it becomes very easy. 64, you can prime factorize it 8, 8, 2, 4, and 2, 4. Well, you can factorize it more, but I need how many 4s? I have 1, 2, and these two together 1. 3 4s. The bases match, so the exponents should equal to each other. That's one thing we do with the exponential functions, or how we solve exponential equations. Now, how do we apply it? How do we apply exponential stuff? One application that we use all the time is called compound interest. This is being used on loans, mortgages, auto loans, any kind of loans. They apply most of the time compound interest. So when they charge you interest on the loan they lend you. So the compound interest, it has a formula that is associated with it. It says A equals P times 1 plus R over N to the NT. What is P here? P is called the principal. R is the rate. R is the rate. T is the time in years. Time in years. A is the future amount. future amount after t years. So the amount will increase to some point. That's after t years. So n is how many times compounded per year? Number of times compounded per year. Compounded per year. So if they say like semi-annually, you know, they tell you semi-annually, this means n is 2 because semi-annually means twice a year. If they say annually, means n is 1. If they say monthly, means n is 12. Now, how do we apply this? How do we apply this to an example? Find the amount when $8,000 is invested at 2.2% compounded monthly. Compounded monthly for 8 years. Okay, for 8 years. Let's see what they give us. So compounded means I'm going to use that formula. So I'm going to use A equals P times 1 plus R over N to the NT. The 8,000, that's the principal. That's the amount that you deposit into the bank, right? And invest at 2.2, so that's R, 2.2%. 2.2% means you're dividing this by 100. Means it's you move the decimal point to the left side 2 times or 2 steps. 8 years, that's the time. So they give us everything. Let's substitute that in. So A equals P is 8,000. 1 plus R is 0.022. N is, wait, did they say annually or something? Oh, it says monthly. So monthly means N is 12. And again 12, and the time is 8 years. Now, how do we calculate this? So when you substitute this in the calculator, the first thing you do is the fraction. So that's the first thing you put on the fraction. Then whatever amount you get, you add it to the 1. That's the second thing to do. So this becomes 8,000. And as I'm putting this in to the calculator, I'm getting this number. And then you can multiply the top ones to get 96. The next thing to do is this. This is the third one. You put that in the calculator as the third one and multiply the result by 8,000. That will give us about, let's see, what would that give us? $9,535. This means you made, how much money you made? You made 9,535 minus what you deposited, which is 8,000. So that gives us $1,535 over 8-year period. And to you, you might say, wait, that's not a lot of money. Well, because the original amount that was deposited was very small. You know, that's why you don't expect a lot of money from a small amount of money. Now, sometimes they say compounded continuously. Compounded continuously. What is compounded continuously? If they ask about compound continuously, we then use this formula, A equals PE to the RT. It's like PERT. So P is the principal, A is the final amount after T years or future amount after T years, R is the rate, T is the time in years. E here is the 2.7 that I introduced earlier in the lesson. And how do we apply this? Let's say we are asked to find the amount when principal of $12,000 is invested at 4% annual rate compounded continuously. For 5 years. So the first thing is compound continuously. That's the key here. That tells us use this formula to find the future amount. So how do we use the formula? The principal is 12,000. E, we keep it as is because on the calculator there's the key E for that. You don't have to put 2.7. R is the principal rate, which is 0.04, and it was 5-year period. So if we try to calculate this, the first thing we would do is we calculate the exponent. You multiply the 0.04 times 5. So I'm assuming you're using a scientific calculator. If you're using graphing calculator, you can just put all of this in one step and it will give you the answer. So when we multiply this out, what we get on the top, we get 0.04 times 5, that's 0.2, and then we're gonna, as the next step, put e to the 0.2 in the calculator, multiply the answer by 12,000, and that will give us about 14,656.83. So this will be the returning amount. That's what we're gonna get in return, or at the end. So the money is gonna grow from 12,000 to $14,656.83. That's another application to it.